So let's see another problem in classical mechanics. So a uniform sphere a uniform spherical shell of radius smaller lying on a rough surface is given a sharp impulse horizontally. So what they are saying the question is, so this is a spherical shell. It is not a sphere, but it is not a solid sphere, but it is a shell, spherical shell, and it is of radius smaller. So here to here radius is smaller, is the radius of the sphere, and it is lying on the rough surface. So this is the rough surface, and it is given a sharp impulse horizontally. So this spherical shell is given a sharp impulse. So just a small force applied for a short duration of time. So that is nothing but impulse. That is FDT is the formula of that. So for a short duration, simply impulse is given. So just like hitting a ball in cricket, like that. So just a if, force applied for a short duration is nothing but impulse. So like that, just a small impulse just from here, a impulse is given. So just we are hitting it for a short duration of time. So that is the question. So if the sharp impulse is given for this sphere, then which are the options correct they are asking out of these four options. So what are the four options given is, irrespective of whether the impulse is given, the shell always slips before pure rolling starts. So it does not depend on impulse. So always it before the spear starts, first the spear would slip, then it would start rolling. So that is the meaning of this. So whether it is true or not, we'll see. And if the impulse is given at a height 2 by 3 into r from the center, then the shell will roll without slipping. So what they are saying is, we are giving the impulse at this much height, that is it is shown in the diagram. So from the center, at this much height from the center, then the shell will roll without slipping. So that means from this much height, so this is the center. So if we just draw a horizontal from center to this much height, so we can apply force from this direction only or from this direction. So suppose if we are applying in this direction, so at certain height from the center, so this is the center, so at certain height we are applying force, or else here like this, here, or else like this. So this is the center at certain height, so this is some particular height, like that we are applying force. So according to the question, if we apply force at this height from the center, then the shell will roll without slipping. That means it would exhibit only pure rolling motion, but it would not skid or slip on the rough surface. So that is the thing they are saying. So we need to see whether it is true or not. So if this is true, this comes out to be true, then this is false. So irrespective of where the impulse is given, the spear always slips before pure rolling starts, they are saying. So wherever we give impulse, whether here we give, here we give, here we give, at this point, wherever point we give, whatever point we would give the impulse, it will shell will roll without slipping, they are saying. So but here what it is saying, this sorry will always slips before rolling starts, they are saying. But here what it is given in the second option, that is B, the shell will roll without slipping. So these are exactly opposite. So if this is true, then this one comes out to be false. And another point what they have given is, if it were a solid sphere, but so actually in the question what it is given, it is a spherical shell, but it is here what they are mentioning is, if it is a solid sphere, if let us suppose if it is a solid sphere, instead of a shell, the height of which the impulse is to be given so that it rolls without slipping, that means the sphere should not slip. It is 2r by 5 from the center. So that one we need to see whether it is true or not. And whether it always slips before rolls or starts rolling immediately depends on the amount of impulse given. So maybe this point also will turn out to be false. So let us see whether, so actually the solution it is given that B and C are the correct options. So it depends from this the rolling of the sphere depends on height, at what height we have applied. So it depends on that height we have applied. So in order to start pure rolling motion, so height matters. So that is the thing from this you can say. So it does not depend on impulse, and it does not depend on so it does not depend on impulse, so it depends on height. So depending on height, the pure rolling will start. That one we need to see. So this is the diagram as we have discussed as earlier. And here, let an impulse integration of f dt be given horizontally at a height h from the center of the sphere. So here they have given the formula for impulse. So integration of f dt is nothing but short for force for a short duration of time. So f could be written as mdv by dt. So dt would get cancelled. Mdv impulse is just like a momentum. It has the dimensions of the momentum. So force for it. So this is the formula for impulse. So this is the impulse they are saying. As a result, let the center of mass of the sphere acquire a velocity v. So because of application of impulse, we are just applying force, short duration force for short duration. Because of this, they are saying center of mass of the sphere acquire a velocity v. That means the center of mass would acquire velocity v. It would acquire velocity because of skidding, or else because of rolling of the sphere. So because of the rolling of the sphere, it would move in this direction. At the same time, because of translational motion, slipperiness, because of slipping also, it would acquire velocity in this direction. So these many conditions are there. So it can acquire because of slipping or else rolling. So it acquires velocity immediately v. So it is disturbed from this rest position because of application of force. And let the sphere acquire an angular velocity omega about the center of sphere. So what they are saying is it is acquiring translational velocity because of motion of the sphere in this direction. So that is nothing but translational motion. That velocity is v, that is decided by the center of mass. And also that rolling velocity, the speed with which the sphere is rolling, that is angular velocity. It rolls with a speed of omega. That one they are saying. So this much angles per second. So we have especially omega 2 pi by t like that. So that means how much time is it taking to cover 2 pi degrees. The 2 pi is nothing but 360 degrees. How much time it is taking, like that. So for one complete revolution is nothing but 2 pi 360 degrees. Hence we have 2 pi by t like that time period. So time taken for one complete revolution. So how much angle it is covering. So for one complete rotation 360 degrees like that. So that is angular velocity. And next thing what we have is torque. Formula of torque. We need to consider formula of torque. Y means here rotational motion is coming into existence. So actually here this is the center of mass point. So at particular distance from the center of mass point we are applying force. So what is torque is nothing but force into perpendicular distance. In general, torque we consider force direction and perpendicular distance direction, especially for maximum. So r cross f, rf sin theta, when theta is 90 degrees. So that is nothing but perpendicularity condition. When r and f, r is position vector, f is the application of force. So if the angle between these both of them is 90 degrees, so then we would have rf sin theta sin 91. So rf force into, that is force into perpendicular distance, like that. So from that we have got, so r cross f, torque tau is equals to dl by dt. Just we have f is equals to dp by dt. Here torque tau is equals to dl by dt in the place of pl. So this is the formula. So from this formula we could acquire this, or else we can say from this formula we can acquire this. So taking torque about the center of mass they are saying. So from this formula if we simplify this formula has shown here. So we could achieve this formula. So they are what they are saying is taking talk about the center of mass. So this is the center of mass. We are considering talk about this center of mass point. So in that case, if we consider, so torque is nothing but force into perpendicular distance. Force is nothing but ma. Yeah, a is nothing but dv by dt. And perpendicular distance here is h. So this is the center of mass point, and we are applying force here. So this is nothing but perpendicular distance from the center of mass point. So this distance is nothing but perpendicular distance. So this height is taken from center of mass point horizontal plane. So that this is nothing but perpendicular distance from the center of mass point. So that is nothing but h. So force into perpendicular distance, and that is nothing but dl by dt. And we know that L is nothing but I omega, just like P is equals to mv. So we have L is equals to I omega. So in the place of PL, in the place of mi, in the place of v omega. So the if we define, however, in inertia is constant for a given object. So whether it is a spherical shell or a solid sphere like that. So I naught is taken out. So actually that is di omega by dt. So I naught could be taken out. So then we would have I naught into d omega by dt like this. So now what we have to do is dt would get cancelled. So what would be remaining is mh dv and I naught d omega. So now what we have to do is integrating on both sides. So if we do integration, so integration of dv is nothing but v. So from initial velocity to from final velocity. So initially as the sphere was at rest, we are giving impulse. So initial velocity is 0. So integration of dv from 0 to v, that is nothing but v. We would have v minus 0. And initially the sphere was not rolling, so its angular velocity is also 0. So integration of d omega is nothing but 0 to omega, the omega minus 0. So we would have I naught omega. So from this formula and this simplification, we would have this term. This is the formula we obtain. So here it is clearly shown in this diagram. So this is the sphere. We are applying impulse at this point, at this particular distance from the center of. So this is that height, perpendicular distance from the center. So because of that, the sphere is moving in the forward direction with velocity. So the center of mass point is moving with velocity v in this direction, and as well as it is rolling like that they have shown. So that is the thing. So next thing is, so for pure rolling to start immediately, v is equals to r omega. So what we are saying is, if it is having a pure rolling motion, if there is a pure rolling motion, what happens means how much it is rolling. So because of its rolling, it would cover certain circumference. So it would travel certain arc length of this sphere. So because of that rolling, so distance traveled by it is equal to circumference it has traveled. Suppose this is some A point, if we consider. So for certain time after, it would move to here. This point would move to here, this A point. So this sphere also would move forward direction. Now at present A point is here. So as this sphere moves like this, rotates like this, rolls like this, so this point would move here and it would have traveled certain distance in the forward. So center of mass point would have traveled certain forward distance. So that if it is a pure rolling, so if it is moving forward only because of rolling, so the how much it has moved from this point to this point, that is nothing but equal to how much this A point has moved from here to here on the circumference of the circle. So that is nothing but pure rolling motion. So that's why in the pure rolling motion we have V is equals to R omega. That is V is equals to R omega. So just like if the sphere travels L length of the arc for this much time t, so that is nothing but velocity. L by T, and it covers, this arc covers theta angle in that time T and R. So Tt would get cancelled. What we would have is theta is equals to L by R. So from that formula we are having this. So in that logically, in that manner, if you think, you would have this. So the from that rotational motion also we would get this. So if V is equals to, pure rolling will start. So the sphere should not slip, it should roll. As soon as we give impulse, it should start rolling without slipping. So that is possible when V is equals to R omega. So now what we have is the mvh, like that we used to keep, and I naught is nothing but 2 by 3 mr square, moment of inertia for a spherical shell, it is 2 by 3 mr square formula. So omega, so in the place of V, R omega we need to substitute. So mm would get cancelled, R 1 R cancel, omega omega would get cancelled. So what would remain is only R, 2 by 3 R. So at this height, if we apply impulse at 2 by 3rd of radius R, at that height if we apply impulse, then pure rolling would take place. And next thing is, so next case is in the case of solid sphere. So this is for a spherical shell, it is. So if we consider the solid sphere, then I naught is goes 2 by 5 mr square. Formula for moment of inertia is 2 by 5 mr square. So if we substitute here, so mvh, so this is mvh, I naught omega. So in the place of I, we need to substitute 2 by 5 mr square. So that is the thing we have done. So mvh in the place of I, that is I omega, I naught omega, so 2 by 5 mr square, and V as usual R omega. So just substituting. So and after cancellation, would get cancelled, R omega, so 2 by 5 R would be remaining. So at this height, in case of solid sphere, this is the height where the pure rolling motion starts. So logically thinking, if we apply for impulse at this point, it would just skid, because we are applying here, it would just make them to move forward, and again because of the roundness of this sphere, pure rolling would start. But that only at some particular height from this distance, if we apply force, means it would result in rotation of this sphere. So then pure rotation will start. We are triggering rotation if we are applying force at some particular height. We are just seems like we are applying triggering rotational motion at certain height, means that only if we apply here, suppose at this point, means so it would first skid, and because of roundness of the sphere, it will start rolling. So that is the because of the shape of the object. So if we consider the in the place, if you consider square shaped body like cube or cuboid, like that. So if we apply force, means impulse, means then it would just skid, but it would not roll. That is because of that shape of that object. But here the sphere rolls because of this roundness. So first of all, it depends on at what height we are applying the force. So if we apply here, seems like we are just making it to move forward, then again rolling motion will pick up. And here if we apply, so seems like we are triggering the rotational motion. So logically if we think, we are just, of course we are making it to move to that side, plus we are, seems like we are applying, we are saying the uh, particle at this point to roll on. So like that, rotational motion would start. So that is the problem. So thank you.